Good afternoon, everybody. Welcome back. Today we are going to discuss about execution level control. See, in mathematical foundation of robotics, we have so far understood many mathematical modeling technique for describing robot in a cyberspace, that is inside computer. Now computers can only solve some problem and give you some output in the form of data. But with that, robot is not going to move, right? So with those planning level instruction in the form of data, what to do next so that a robot will actually move is the area of interest for execution level control, or the domain of execution level control, right? So that means robot is solving the inverse kinematics problem, say, of a Baxter type of robot. Now, once those joint values are known, then those will be input to the execution level control, and the job of execution level control is to make robot move in those predicted joint angles. So that's very important, and that's what we are going to discuss in my subsequent lectures, where we will try to give you concept of execution level control. We are calling it execution level control. So computer is a controller also, right? That is a planning level controller. You are solving programming, you are running some algorithm, getting some result. So those are called planning level control. After getting those output in the planning level control, that will be fed as an input to the another controller, which is known as execution level controller, right? Which actually will execute the task, and that will make your robot move in a desired fashion, right? And execution level control, that means control system engineering, is a very, very vast area. I used to teach once the computer control system, and this was my textbook, preferred textbook, what I have shown here. This one, Control System Engineering by Norman S. Nice. Also, there is one reference book you can use it, Modern Control System by R.C. Dolph. But these are actually one semester long courses, okay? Or maybe running in 2 semesters if you 2 semesters if you want to go sufficient deeper. But here we'll be very briefly describing the execution level control to the extent which is required for robotics application. So let us start from the very basic, that what is a control? Control means, that means execution level control means getting some action, and with those action making your system to reach to the desired state. Who will give this desired state in case of robot? Is a high level control, or sometimes computer control we call high level control, and this type of control is called execution level control. The high level control cannot execute the task, it can only give instruction, okay? So execution level control will follow the order of planning level control, and planning level control will give you desired state. Execution level controller will try to follow the desired state, and the theory behind it, mechanism behind it, is the domain of control. So what is control? Control is nothing but sensing and acting, okay? So in very sensing and acting so as to reach to the desired state. That means control will have some kind of sensor, unless it is a bang bang type control or on off type of control. That means Say for example, you are switching on your fan, or switching on your air conditioner, or switching on your heater. Okay, so unless they are having sensor um, to set a particular value or particular RPM, so those are known as on-off control or bang-bang control. So there is a jargon term. So control maybe two types: bang-bang control, bang-bang, or on-off control. Okay, and fairly regularly we use this, right? When we are feeling discomfort, we are switching on our uh, fan, and fan started moving with a desired uh, or set RPM. Okay, that's why it is called bang bang control, because once the switch is on, you cannot do any control, you cannot take any control action. So control action has been taken at the design level. For example, the some fan of some brand name, it has rated RPM in when you switch on. So since you believe that brand, it is supposed to rotate at that RPM or revolve at that RPM. Of course, there are some discrete. Now I am calling you, introducing with some jargon term. There are some um, speed controller, motor that fan speed controller. Okay, they are discrete in nature. Sometimes nowadays, of course, potentiometer type of sensors are there, so they are also continuous control, where you can just increase the RPM or decrease the RPM, but getting it as a set point. For example, I want exactly fan to rotate at n RPM requires more sophisticated control action, not bang bang control, and that will be precisely the um, uh, the agenda of our discussion. Okay, so the control necessarily means you will have to have some sensor, you will have to have some desired value, and you will have to take some action sensing the state, and you know from the sensor what is the current state, you know from the planner what is the desired state, and if there is any difference, then you will take some control action so that your state can reach very soon to the desired state. This is actually control. Now, in describing control, going in further detail about control, we will talk about mm, uh, some uh, some terminology and some terms which are basic uh, necessity for understanding a control, right? So, a control will have sensor, actuators, sensors, actuators, okay, and action rules. Basically, these are the three things every controller should have. And control can be of two type. One is bang bang open loop control types. Uh, open loop control, and then you have feedback control. Okay, the example I just gave, that you have a fan or you have a air conditioner and just you switch on, is an example of open loop control. So in the simplest architectural drawing, if I present here, so this is your input, this is your output, and this is called transfer function. transfer function. Try to understand. This is open loop control, right? Input, transfer function, output. Try to understand each terms here. So, in case of a motor control, which is very, very common, transfer function means you have a relation, a function, okay, which consists of number of turns of the motor, say an armature current, armature voltage, line current, line voltage, what else? And anything if I am missing, all the parameter with which you have made a model, okay, and you input, say, some armature current you feed, and here you get rotation, RPM. So motor shaft, if this is a motor, so motor will rotate, okay, and you know motor has stator, rotor, okay, and in the you have turns, multiple turns of wire in the rotor, okay, which is actually becoming an electromagnet, and then it is rotating within another magnet and all kinds of things, basic principles you know. But this is the transfer function. What it does, transfer function creates a functional relation taking into account of all these parameters: armature current, armature voltage, line current, and number of turns. Based on that, you will get rotation in the, and actually if you just put some sensor, you will get some torque, which will eventually rotate the motor. Okay, so you increase armature current, torque may be increased. Decrease, torque will decrease, of course, up to certain point. And why armature current? Why not armature voltage, line voltage? Yeah, mathematically possible. All the parameters are can be controlled mathematically, but controllability is an issue. That means which parameter I should use for running my motor, okay, in when I will apply control strategy is very important. It turns out that armature current is very easy to control. That's why I have written here at armature current. So in case of open loop control, in case of say fan motor, you have some mathematical relation and you have some line here. In case of fan example, it could be a line voltage which you apply, okay, so and you will get some so line voltage is also there, you apply that voltage and it will be rotated, right? So mathematically everything is possible to be controlled, and depending on our requirement we apply control strategy. So what is transfer function? Transfer function is actually taking input, transferring from one domain to another domain. You see, this is electrical domain, right? Current, voltage, all kind of thing. Eh? So this is taking those energy as an input, electrical energy as an input, and this is a model, okay, that is relation between all the parameters, okay, and then at the output you are getting mechanical energy in the form of rotation. So that's why it is transferring electrical energy to mechanical energy, and that's why it is called transfer function. So always it will transform from one kind of state to another kind of state. Okay, so this is also open loop control, because I know if I put this much of input times this transfer function will be my output. Whether we are getting that or not, we are not concerned about that, then it is called, then we do not take any corrective action, then it is called open loop control system. Okay, and more pictorially I will show them in this form in a generalized way. Okay, so this is input, this is output, and this is transfer function. So GS is the transfer function. Why S is there, we will discuss later on. Now you see, this is open loop control. What is feedback control? Suppose I have now more money and more requirement I need. So I buy some motor, I just install it, and then I switch on, and I expect the motor will be rotated with that much of speed. And I do not care whether exactly that speed I'm getting or not. But in many cases, this is not the case. If I have input and I have some desired output, okay, so I will have to have that desired output. Okay, sometimes output is also written as Y, okay, or O, right? So what I will have to do in that case, if I require that stringently I should get Y, that is desired value, then I will have to see what actually I am getting. Okay, so I will have to have some sensor which will sense my output, and then sensor will, the moment sensor is giving me that this is actually what sensing is actually Y, actual Y. Okay, so I can have another action, okay, and either I will have to compensate, okay, till YA output, actual output, and desired output actually becomes almost equal. Okay, so what you have, I have sensor, and I'll have to have some action. Okay, action, so that my actuator here, it is says motor, sensor, another transfer function, because that is the control action I am taking, and then I am again compensating it and getting, not stopping. Okay, again and again I am doing this in an iterative way till my Y actual, Y desired becomes almost equal. So this is a concept, this is a feedback control. Why it is called feedback control? Because I am taking feedback. I don't believe anymore what is the output, whether that is a desired out, matching with the desired output or not. So I will take feedback with the help of a sensor, and I will have to make sure that here, so what is the signal here? Called error. Okay, this is equals to, you see, I minus, everything we will talk about is minus HS. So this is called error signal. Okay, and this error has to be compensated. So error is a signal, and according to that error signal, if it's big, it's small, take different kind of action. Those are called control action. Okay, there are various kind of control action. We will talk about those things in robotics. Most prevalent one is PD and PID, proportional derivative, proportional integral derivative, proportional derivative integral, right? What are those? Proportional to what? Proportional to error. Integration of what? Integration of error. D is what? Derivative of the error, rate of change of the error. So all this, if I can sense, and I can take control action not only on error but also on these values, that might be taking my controller towards very stable zone. So I can introduce you with the concept of stability. Okay, so I will have to make a controller which is stable, means in no time, as minimum as possible time it should take, and it should actually take my controller to the desired value. Okay, so this is very briefly what control is. So control is very humanoid way. We also control, like our brain is a thinker. Say I am now mm, intend to write some trajectory, follow some trajectory, right? So say control C. So this is C, right? So this is my desired C. Who told me that this is desired C? Based on my experience, based on my learning. Okay, when I was a child, my mom actually um, told me that this is A, this is B, this is C, all kind of thing, right? So in a supervised way, I learned. But in case of a robot, you will see the controller need to have all those philosophically similar kind of thing. So to follow this trajectory, controller need to have a sensor. It will start from somewhere, and if this is a given trajectory, my controller is expected to give some kind of C, right? And depending on kind of sophistication your controller have, it could be something like this. Okay, it could be this, or it could be exactly this. Okay, exactly matching with the desired value. So we'll talk about all this. Okay, so controller actually ensures that desired state is being achieved. Now we'll take a digression from here for further understanding of control in a very nutshell, right? These are in a ridiculously simple way we are trying to understand control concepts which will be applicable to robots. Okay, so that's our intention. So before taking any time, we are going to introduce you with a second order system. Okay, what is a second order system? This is, I believe, is the kernel of control. So without having detailed concept of what second order system is, it is extremely difficult for anybody to understand control. So in the next class, I will go some detail with second order system, detailed analysis of a second order system. The more clearly we understand second order system, more clearly we'll be able to understand the control theory and practice, and everything will be very easy. So till then, stay safe. There is a new variant now of coronavirus. Be careful. Don't take it easy, and altogether we will win over coronavirus. Till then, I wish you will be on campus very soon. Have a nice day. Bye bye.